Hello, my friends. This is Dr. Mohamed Nezami again with another lecture on the design and 3D modeling of RF and microwave devices. This is the second part of two parts on the design and modeling of comp line or cavity, coaxial cavity filters. And we focused on both the comp line and the interdigital. Last time we covered basically the use of the comp line filters and interdigital filters, the cavity, coaxial cavity, and we showed a lot of them where they were used. We showed some of their characteristics. You can refer back to part one. So today we're gonna just to refresh your memory back. We are covering the design and construction of the comp line and the interdigital filter, and both have quarter wave resonators, okay, tuned via an end capacitance using screws, okay, and so let's go further. So here we are. Now, the design of these filters is basically done in HFSS, at least on my end, but it can be done with CTS or any other European packages. Today, we're going to cover several of those filters, starting out with this one here. This is a 2466 section comp line filter. Okay, this comp line starts out with the basically the coaxial connector on this side. There is the outer shield. There is the inner Teflon material, and the inner connector is attached to the first resonator. Okay, same thing done on the output. Okay, the resonators are not, in this particular example here, they're not tuned via any incapacitances. Okay, so this is just basically fixed length in here. The second example, I have the same exact filter except implemented a little different. Okay, this is the very much the same filter, except what I did here is I used basically the air vacuum inside as my outer construction of the resonators, and I basically made it into a perfect conductor, a boundary. I set the boundary for this here. Okay, here are the resonators inside, and then I set also the suction in here, which is just a lead. Okay, and this is just to show you the differences between this and this. This here is more realistic if you want to fabricate this, because it has the actual aluminum enclosure, okay, where the other one doesn't. Okay, and it's up to you to use either one. The second example basically is this here, and what this is, it's a cavity, coaxial cavity filter, except this one here, I'm using a set of adjustments, tuning adjustments. So we have 2, 4, this is fifth order. I have the resonators in here, and what I have these tuning screws modeled as cylinders right across from each resonator. Okay, and then I also have these other inter-resonator tuning suctions. These are basically the tuning screws, and they're basically, these are to tune the bandwidth actually, because they control the coupling between the inner stages of the resonators, and that does tune the bandwidth. Where the other ones, the ones across from the resonator, this one here, basically controls the capacitances. And so therefore, this one here really moves the center frequency of the filter. The other example I have, okay, I have another example, which is a simple fourth order filter, okay, and in this one, I'm using only tuning elements that would actually tune the bandwidth. So this is fixed resonator height, length, okay? But what I have in there is I introduced a set of poles, the screws that tune the coupling between the stages. So let's get back to the lecture and resume where we were. Okay, we covered basically. We said that this is the comb filter, and like I said in the beginning, these ones in here, these actually these are the coupling screws, adjustments, and then we have the tuning screws for the center frequency. And this is for the bandwidth. And this is how the filter look like. And in this construction in here, what we do is we utilize this tuning screw in here. There's a groove inside the resonator, and this tuning screw actually go into this and acts as shown right here as a capacitor filter. This is a coaxial capacitor filter where the charges are stored between the inner and outer shield, okay? And so the depth of how deep you can go into this controls the capacitance. And the reason to do it this way rather than doing it and this is how physically it's done. So you can see the groove is here, and so this screw just goes in and out. Okay, so let's cover the theory, some of the theory work that goes behind this. First of all, let's just look at the top level approach of how you would design these. Starting out from the beginning, okay, you're giving a set of specifications. It said, I need a filter, center frequency at this frequency, 3 dB bandwidth is this much between these 2 points. This is how much insertion loss, the rejection band specifications, and so forth. You might specify the group delay in some instances. So you go in and you synthesize a filter using the polynomial Chebyshev and Bessel tables, okay? And then you end up with a low-pass filter that has coefficients, okay, that represents basically lumped elements. And the input and output are normalized to 1 ohm usually, okay? And then from there, you transform that onto a bandpass filter, and then you can optimize it. Actually, you can optimize it using tweaking the lumped element in there. The lumped elements are not real, of course, because you have to replace those by resonators, okay? So, and then you say, okay, now I'm ready. I need to realize this filter physically into a comb line filter or into an interdigital filter. So you come in, the first thing you would do, of course, is you build a single cell resonator, because you know what the center frequency is, so you can right away decide what the length of the resonator is. And then we have the impedance of this resonator, the coaxial resonator. The characteristic impedance usually, like we said, we detailed in the first part of this presentation, it's set to 77 ohms, which coincides with the ratio between the inner diameter and the outer diameter of the coaxial section being at 3.6, the ratio, okay? So doing that, the first stage, we construct a single resonator to obtain the right resonant frequency, characteristic impedance, and the unloaded Q. So how do you go from here and find out the unloaded Q? I'm going to present that to you, a few of these approaches, but the first approach uses basically a EM modeling, HFSS simulator. We use the eigenmode calculator to actually model the resonance and see what the resonant frequencies is at, what the Q factor is. And the eigenmode value, basically, it's a modeling technique where you can look at a structure like this without driving any waves to it, without any ports. It goes in, and depending on the materials, the geometries, it can decide what it can actually estimate what or calculates the resonances of this structure, and many of them, of course, not just the lowest mode, but it will also go out and compute up to a certain number of modes, the resonances. The second thing we need to do is we basically construct the input and output coupling to obtain the loaded Q factor. So in this first one, we use it to design the resonator and optimize the length of this inner and outer parts of the resonator, and we compute the Q factor. And if we're satisfied, now we can go in and actually attach ports to this, and again model the center frequency, and also decide on the loaded Q factor. That means the Q of the resonance of the resonator, once you attach ports to it, it gets loaded down by the external by the input and output, and the loaded Q factor comes into play. Okay, and then what we'll do is we would go out and construct the coupling between the adjacent resonators. So, and then we can go in to construct two of these resonators. And then in this case, of course, we can use lightly coupling, meaning we don't attach the ports to the resonators so that we don't load them. So we just kind of sense what the Q and the center frequency, because those really don't, the insertion loss doesn't come to play in there. There's a technique that you can estimate the Q and this, and of course, visually see where the center frequency is at. Also, you could do that to a single cell. You could actually take a single cell and only attach one port and then couple lightly from it to an output port and estimate the external Q of this resonator. Also, another thing that I talked about earlier is the capacitances. How do you load this resonator with a little screw in there that goes in and out of the groove that's inside of this? So we'll look at that as well. So once we construct the coupling between two adjacent ones, and then we're ready to actually go ahead and construct the whole filter. So these here, the first few things, basically, once you're past that stage, you're almost done. So you construct this, you come up with the initial dimensions, and of course now the filter will be detuned and it won't have the satisfactory performance. But you can go in and actually get the optimizer. You can parameterize all these dimensions from the beginning, of course, make them variables. And then you can come in to the optimizer and say, I want to optimize the filter so I can have the insertion loss in this frequency band this much, and the rejection loss, and as a function of varying all these lengths. Now, one of the things that I forgot to mention is how do you basically match this filter? And that's where this coupling point here, how do you decide on where to tap the filter onto the resonator? And that is done computationally. And then once you do that, you verify it via modeling. So you can come in actually and sweep this distance from the ground end to the inner conductor in here and get a sort of like a minimum loss, perfect or close to perfect impedance matching. Okay, so just looking at the now, you could do that to capacitive coupled resonators as well, where the input and output mode. So we have, again, we have the diameter of the outer shield for the resonator and the inner. And then we have also the iris windows in here that determines the coupling between the adjacent resonators. And then we have other things as well. So we have to optimize the height of the cavity, the length of the resonators, and several other things that we will show. Now, just to show you how do we start designing the first step, which is how do you design the basic cell resonators. And I want to refer you to Dr. Stephen Remillard on the YouTube channel, and this is his website, his channel on YouTube. And I took this diagram from him, and basically he has a real nice several lectures or presentations on designing coaxial air-filled cavity, and he derives the Q factors, both loaded and unloaded, and it's you can refer to it. But what the takeaway from his lectures is that we have a resonator in here, and we have now it's shorted on this end, and it's open on this end, this one here. So we need to decide it has a certain length and a certain radius, which is we call A, and the outer shield of the cavity has a radius of B. Now theoretically, we can, from the theory of quarter wavelength lines, you can see that the resonance frequency actually comes in as the speed of light divided by 4 times the length. Okay, and that resonance actually repeats at every odd number, meaning that if this resonated at 1 gigahertz, the next resonance would be 3 gigahertz, the one after that would be 5 gigahertz and 7 gigahertz and so on. But what we came up with is that the another thing to also consider is actually this B dimension in here. We know that the ratio, we want the characteristic impedance of this line to be 77 ohms. We did cover that in the first lecture, and I will also represent some of that again, just to show you where that number comes from. So we know the ratio of B to A is about 3.6 to produce 77 ohm coaxial line, okay? And then we have this here, which says that the B dimension has to always be chosen at least that much, which is the air wavelength divided by 12, okay, or 1/10 of a wavelength. Okay, so we want this 1/10 of a wavelength, and this emanates from the condition to have to assure that you won't have any of the higher order mode propagating in this resonator. So this here was the slide that we grabbed from the initial studies on coaxial lines, where we said that early on in the century, when they invented coaxial lines, they derived the characteristic impedance as being this much, which is the natural log of the outer diameter to the inner diameter, okay, multiplied by this factor, which is 60 divided by the square root of epsilon r. Of course, epsilon r in this case, it's 1 because it's air filled. And when they swap this, okay, with the ratio of this much and see where that ends up being, they get a curve like this for the Q factor, the unloaded Q, and they found that it coincides with the ratio when D over D, capital D over the outer diameter to the inner diameter ratio being 3.6, the characteristic impedance was 77 ohms, okay? And the Q factor was the maximum, okay? In this case, about 3,400. So, and we did show that that's why the coaxial lines for cable TV and long distance coaxial line communications use 75 ohms because that's the least copper loss that or transmission loss that you would get. Okay, so in these filters that we're going to talk about, we will always use 77 ohms as being the characteristic impedance, somewhere in the 70s. It doesn't matter. It could have been 75, 70 is okay. Now, the resonators themselves, a lot of times they could be either a square in this case, or rounded, circular, or cylindrical, or square. Okay, these are the resonators. And as you know, from the area of a circle to the area of a square, now the area of a circle is pi r square in this case, or pi d over 2 square. And the area of a square is basically the length times the width, which is d square. If you take the ratio, it comes out that you have a pi over 4 difference between whether you have a square geometry, coaxial cavity, or to a cylindrical coaxial cavity. So therefore, the impedance, when you're computing the characteristic impedance, all you need to do is use exactly the same as cylindrical, except plug 4 over pi in the inner, the ratio in this case, okay? Now, let's start looking at some, trace back using 77 ohm, which is the optimal characteristic impedance for the maximum Q. What is the ratio of the inner to the outer, or the outer to the inner? And that can be looked at from here. Okay, so we have characteristic impedance equal to about 60 times the natural log of B over E. Okay, so if we set this here to 70 ohm, or 77 in this case, okay, and solve for B over E, it turns out that B over E is equal to 3.6. Okay, so that will be used as a design parameter. Let's take an example. Okay, so we've got this resonator. Okay, and what we do, we leave out a little bit of a gap between it and the outer side, the ground, which is grounded. Okay, which we call the G in this case. So we need to calculate for 2 gigahertz what are the dimensions of this cavity. Okay, we start out saying, okay, the characteristic impedance we know is 77. We know that we want the outer cylinder to have a radius of at least, or the diameter is at least lambda 0 over 12. Okay, if you solve lambda 0 for 2 gigahertz, you get 15 centimeters. Okay, now, and of course, B over A, we know that it has to be 3.6. So automatically, if that's the case, then automatically we can come in and say, well, we know that B has to be this much here, 15 centimeter divided by 12, which is 12.5 millimeter. So that gives you a solution for A. Then A is 3.47 millimeter. So we've got the diameter of the inner, the diameter of the outer. Okay, these are set. Now we need to turn to calculate the length of this. We know obviously the quarter wavelength, we know what that should be, which is this divided by 4. Okay, but what we need to do in here, in this case, we know that we're going to have a capacitance in here that will, if we design this exactly a quarter wavelength, we will never resonate at the desired frequency because of this capacitance. So what we're going to do, and we mentioned that earlier in the lecture in the part 1, is that usually designers come in and say, let's make the inner length, the length of the inner conductor, the resonator, being somewhere between 30 to 60 degrees. In this case, 60 degrees is like 1.0472 radiances. So so we want this length here to be 60 degrees electrical length, and that corresponds to 25 millimeters. at 2 gigahertz, okay? Now, if you wanted to make it a quarter wavelength, okay, so you solve this equation, which we showed earlier, okay, and in that case, it would be 37.5 millimeter. So you can actually, you can go to the HFSS and actually see where that resonator, let's take it, okay, let me show you which one, okay. Okay. So we're going to take the resonator and put the model for it. Okay, here it is. So here's the resonator, okay, and the dimensions of this, basically if you look at the dimensions of the pole in here, the center pole, this one here, it's exactly 25 millimeters, okay? So you set it to 25 millimeters, set the height of this, the length of this resonator, and the radius is 3.47, which is what we found on these ones here, 3.47 and 25 millimeters. And now, so how do we verify that this is really going to resonate at 2 gigahertz? So basically, we're going to put it, and then we're going to put the set up a analysis, okay, which is basically an eigenmode solution, where we're going to set the lowest frequency, and we're going to set 5 different modes, and then we solve for it. And once we do that, we can look at the results. And here's the results that shows basically the modes, the frequencies, and the Q. And we come in here, and there you go, 2.48 gigahertz. That's the first resonance at 3,773. That's the Q factor. Okay, so indeed, this did work. We could run the electromagnetic field at this, and we can see that, you know, that pattern. As you can see, this is on this end, of course, it's shorted. You won't have any E field. You'll have the maximum field is where the end here. So this is nice. You could come in actually, and since there's a relationship between the H field and the E field, you know, one is the derivative of the other one. So if the one is sinusoidal, one is cosinusoidal. So in this case, in this one here, we start at 0 dimension and then move forward in the Z direction to a length of L. The E field at distance 0 is shorted, will be minimum. And then the H field will be the opposite. So we can go ahead and check that. And hopefully we're going to get that. So we're going to come in here, instead of magnitude of E, we're going to say magnitude of H and apply that. And there you go. Here is the solution did not converge, but you can see that the H field actually maximum is on this end. Okay. So now we're set with this. So if you're not happy with this, yeah, I know we resonated at 2.4 gig. So what you could do is you could reduce, or you could increase the length of this to bring it down to 2 gigahertz, but we don't want to do that. We want it to be at a higher frequency. It's purposely because we're going to have some capacitance to introduce from the, as you can see here, the distance is a large distance in here. So the capacitance in here is at minimum, okay? So if you introduce any kind of tuning metal in here, the cross-section metal, the overlap cross-section of that metal with the end of the resonator will act as a capacitor, will bring the frequency down. So we're going to use this as is and have in mind that this is really resonating at 2.4, and we know that it's going to shift down. So hopefully that shift will bring it close to 2 gigahertz, okay? So let's go back to this. Next is, of course, in the prior days to EM modeling methods, people used to construct these and test them actually. Okay, so what people did is that they would construct a single cell and measure the Q and the bandwidth and all these things, and then go and build the rest of the filter, increase the order of that filter. So people have came in, and this is again from Stephen Rimler. So what we could do is we could actually look at either S21 or S11, and we can actually compute the loaded Q and the unloaded Q by techniques where we would lightly couple either one port or two ports. Okay, and I will show that in a minute. So you basically come in here and you determine where the 3 dB point is and the ratio of the resonance frequency to the bandwidth, the 3 dB band, that gives you the loaded Q. And you can run it in the simulator, find what the compute the S parameters and do this here. Or you could do it from the input return loss from S11. And it works out the same thing, that you can actually do as the unloaded Q. In fact, you could do the unloaded Q not just from S parameters, but from the group delay associated with the return loss. And if you want to understand how that works, the physics of that, please refer to this gentleman here, Dr. Stephen Rimler, and you can watch his videos, and he derives all of that. Okay? And the third method, of course, which we just did, which is find the eigenvalue of the filter. So this is another set of equations that Rimler has, where he goes in and actually from S21 and S22, he looks in there and he finds actually the loaded and unloaded Qs. You can refer to this. So let's shift now back to how do we determine the length of the resonator, because that's very important, you know. So we know that we can determine the inner and outer diameters of this resonator. It's air-filled. The length, we can set the length, but we need to make sure that once we constructed this filter, we put screws in and not realize that, hey, we can't really get down to where we want. It's always, the center of frequency is always way above the physical length of there is no adjustments. You have to go in and again refab the cavity with shorter, with longer, resonator and longer outer. The theory is that once we have a resonator that resonates at a certain frequency with the length L, and the electrical length is 2 pi over lambda time L is equal to phi here, in which case you just saw that we use 60 degrees for that, okay? And 60 degrees is not 90 degrees, so we're gonna preserve the 30 degrees for the capacitors to pull in the resonance of this cavity filter. So that's the approach that you're going to design. So how are you going to do the variable capacitor is basically with this screw that screws in and out of here, and which you just saw that here everywhere. So here it is. You can see that there's a screw that goes in, and it basically this resonator in here resonates at a higher frequency, and we need to bring it down. So we bring in more capacitance to this, and hopefully we go on and tweak every one of these. That's in this case, of course, interdigital, but for compliant filter, we would basically do this same thing. Let's look at this diagram here. So we would do this at every one of these, okay? Okay, so now again, so we have this. Now, how do we go from here on? Well, we know that the capacitance from physics days in high school is really proportional to some permittivity and of the capacitor material multiplied by the area of the cross section of the plates divided by the distance between the two plates, okay? And in this case, so we have, this is the filter. It's the the overlapped area, cross-sectional area between the resonator and the ground in here, which has a height of G, okay? This is really what creates that capacitor, okay? So the capacitor is proportional to the overlapping cross-sectional area and inversely proportional to the gap size G, okay? Now, to increase the capacitance, we need to decrease the gap, okay? And reducing G, basically, or the cross-sectional area, okay? The cross-sectional area in this case, if we have a case like this, we really can't do anything about it because it's a screw, or you can do, actually, you can change the diameter of the screw. That does change the cross-sectional area, okay, to a certain extent. Okay, so here is how physically most of these filters are implemented. Now, so we've got a screw that you come in here from the side and drill down and have it right against the resonator. And you can tune this resonator, the electrical length of this resonator, you can change it by adding more or less capacitance using this screw, okay? And another technique which they use, so if you do this, let's look at the blue line, and I took this out of the IEEE conference papers. Unfortunately, I didn't copy here. I could always give you the reference to this. So you can see that the distance G in here, if you vary the distance of G, okay, as you decrease G, your resonance frequency comes down. You bring it down, so increase capacitance, and therefore you decrease the resonance frequency. And you can see that at a certain portion of this, the curve is flat. It's almost, you have to keep tweaking, and you don't see any result until you get to this area where it's a cliff, basically. And so it becomes a real touchy. It becomes really touchy. Sometimes you vibrate this filter a little bit on the table, and you can see that the resonance has shifted because it's so sensitive. So then somebody looked at this and figured, well, is to what we need to do, we will put a groove into the center resonator. And so the screw, once it comes in, it goes in here, it actually has more cross-sectional area, and therefore we can actually have more linear variation of changing the gap, in this case, G1, okay? As we vary G1, you can see that the ratio between 0.5 to 3 millimeter in this case, okay? That changes the frequency, say, from 1.788 to around 2.2 gigahertz linearly, okay? So you can see that you can tweak it with a screwdriver, and you can bring this nicely to this. And there are a bunch of papers on this. Just type designing coaxial resonators with groove in the resonator to vary the capacitance, okay? So let's see how we compute. Sometimes, even though it's really hard to, you can compute the required capacitance for a certain length of a resonator, but really, how do you compute? How do you figure what the dimensions need to be to get to these dimensions, basically, that will correspond to a certain capacitance? That's really difficult. So, but theoretically, anyway, just to show analytically how this behaves. So you've got a resonator that is somewhere between 45 to 60, 30 to 60 degrees, okay? The electrical length is this much, okay? And we have a capacitor in here because of that screw. So we need the susceptance of the cap and the susceptance of the line to cancel each other, because that's where it will resonate, really, okay? Which means that if you look at the impedance of this, which is the susceptance, you've got J omega C for the capacitor plus 1 over J Z0 tangent 2 pi over lambda L. That's the quarter wavelength shorted line impedance, okay? We need the summation of this equal to 0. Of course, Z0, characteristic impedance is 77. Okay, I'm sorry, this is Y0 here. It's not Z0. So therefore, we can actually solve for this to compute the C in here, the required C. And in this case, it turns out it's really equal 1 over characteristic impedance with the radiance resonant frequency times the tangent of the angle, okay? So it's straightforward. That's the physics of this. But how do you really, can you really use that number? That's pretty difficult. So we rely on simulations to really give us a range of that. So anyway, so again, so let's take an example. Okay, so we're going to assume this with a 60-degree resonator length. And we're going to come in and say, what is the capacitance that is needed to resonate this at 2 gigahertz, like we did before, 2 gigahertz. And it turns out it's about 0.6 picofarads, okay? Of course, if you were to solve this for 90 degree, if this was to be 90 degree, then the capacitance would have to be 0 in this case, okay? All right, so again, let's go back to the filter synthesis, which we mentioned at the beginning. So way back at the beginning of the work that you would do to design one of these. Before we do that, let's look at the simulator. So what I have in here, we have basically, let's look at the one that where we model the groove. So you can see that here is the model of the resonator with the screw, with a groove in here. And I took this and we basically simulated this, model this, and you can see that the, okay, so we can see that the capacitance actually, you can go in and change that, the depth of that screw, okay, and then see how the frequency changes. And let me just show you a plot of that. And that's basically this here. For instance, you can see that if I have the screw way out here, almost it's 0 length into the cavity, you resonate at basically this frequency. And as soon as you bring it to the minimum distance tolerance that you would have from touching the resonator, you end up in here. And in this case, you're between 2 points. This is 1.5 gigahertz, and this is 2.7 gigahertz. So you can see that for a filter at 2 gigahertz, it's beautiful because you can actually have a huge room to play with this, okay? So, so back to this here, what we just mentioned, starting out from these tables for filters, you know, these tables, when we synthesize the filter, you come in and you have a certain table built up. These are from Matthew's book. You can all go to it, standard book, or any filter book. You can see these in. They're listed for certain ripple and return loss and VSWR and certain order and certain percentage bandwidth. And all you need to do, you come in here and you figure out what is the order that you need and then get those coefficients. And those coefficients, we call them the G's. From them, you can decide what the coupling parameters are. And in this case, the order is 6 order. So, and of course, this is symmetrical filter. When we say 6, that means there's only 3 unique values. The other 3 are the same. It's mirror imaged right at, around the center resonator. And you can actually see that the Q external and the unloaded Q play a role in the bandwidth and in the insertion loss. So that's why it's so important to find these parameters here. And once you physically put the filter, you want to make sure that these are actually the same as being modeled before you build it. And same thing for the Qs. Now, the overall Q, of course, the loaded Q is basically the unloaded resonator Q, which we get from the eigenmodes, okay, in parallel. It's almost as the equivalency of a parallel resistor between the natural Q and the external Q, okay? And the external Q, of course, we said that there is a way to get it from basically the group delay of S11 at the center frequency. Okay. So once you do that, of course, you get this one in here. You hook it up together, and once it's loaded, you want to make sure that it resonates correctly. So we can come in here and say we want to look at not this one. This one's lightly coupled, but here is this one. Okay, where we put a single resonator, and then we basically run the simulations and check where the Q is. In this case, 2.7. And what did we get when it was, this is 2.7 loaded physically, of course. Okay, so, and then, so you can verify that is the case without any tuning, of course. And then you can actually put the external from S11, so you can come in and go in with one port only to the resonator and lightly couple from it, and actually estimate the external Q as well. So that's basically this here. As you can see, the resonator in here was connected to the input. Okay, but the output we put lightly coupled, and because we don't want to load it. Okay, and if you look at this, usually what you want to do is you can compute the 3 dB bandwidth, and you need to be at least 20 dB down, because how much coupling do you want to get? You want to get close enough to get a signal, but you don't want to load it. So the rule of thumb from people in this field is that is always the center. If the attenuation is at least say 20 dB or 25 dB, even some case, a lot of people ask for 25 dB. You can get that. Okay, so that gives you the external Q. Okay, the group delay Q, you can get that from basically looking at the same one in here, except looking at the external, the group delay. And I think I did that here. Let's see. Well, we can plot the group delay. Group delay S11. And that's what it is at this here, of course. There you go. No, this is 2 ports, so we can't do it at 2 ports. It's the other one, not this one. Okay. It's not this one. Not this one. It is this one. Okay, so let's look at this one. I think I already calculated that, looked at that earlier. Okay. This is this one, right? So, here it is. Okay, so the group delay. Okay, there you go. So this is the group delay, okay, which is in this case, the 3.7 nanoseconds. So you take this number and you plug it into this equation, and you can solve for the external Q. So there are, as you can see, there are 3 different methods to calculate. So now the capacitance, we covered that. Okay. Okay. So now once we do all of these, of course, initially we would have the tapping point on the resonators is at a place such that you have basically the maximum return loss, and therefore you can actually come in and vary, sweep or tune the input height of the tapping point from the short end, so that you can look at these and you can see that here's this one is the high skew, so you can, even though it's shifted, so but that's okay, but it has the best return loss. So once it shifts, you can go back and tune it with the capacitor to the center frequency and end up and say, okay, freeze that right there. That's the distance. That's what I needed at. Okay. The intercoupling, of course, you do it this way. Okay. Well, no, this one is to just verify the center frequency where it's at, and the coupling between the resonators is usually done by looking at the input and output relationship that is like this. So there's a formula, which is the coupling is this distance from here over the bandwidth. Okay, so what we do, we couple lightly. As you can see in here, these are at minus 12 dB. Probably you need to be a little bit more than that. Probably 25 dB you need to be. So you need to actually pull back the center conductor in here so you can unload a little bit more. Okay, so let's look at the these filters that I have that we started with. So starting with this filter here, put this filter in here. We got all the diameter, all the dimensions are parametrically set, and so you can come in and tune or optimize these. And so this first one, just to show you the response of this filter. This is the response of this filter as is right now as a first shot at this. Of course, as you can see, it's not really acceptable 100%. We need to have the return loss, and the you can see that one of the resonators is misplaced. Okay, so clearly from here, this big dip in here. So the thing we need to do in this case is come in here, and actually we need to set the optimizer for the resonator length. We don't have any tuning capacitors in here, so we have to rely on basically optimizing the length of these resonators. Okay, so let's look at the second case, which is this. Okay, and I think I may have tuned this already. So let's look at the frequency response. It's not 100% good, but you can see that we got the pass band is good, looks good. The ripple is might be okay, but the return loss is not the greatest. You can see that there is potential that you need to bring the return loss of at least say 12 dB down to minus 12 dB down from this point. So it needs a little bit more work. Okay, just out of curiosity, just show you what does the E field look like on these. How does this filter work really? And let's just see the animation of the E field on this, just to show you how it operates. So theoretically, you feed the signal from one end, it starts propagating into these resonators, and each resonator will couple to the other one, and other one, and other one, as you can see. And if you happen to be at the right frequency, of course, the maximum E field would have to be right at the tops, because that's where it will be open circuited and will have the highest E field. And it will couple to the next one with minimal loss, and then the next one will couple to the other one and couple to the other one. Now, if it's not at a resonance frequency, of course, this will be loaded. It'll have an impedance, whether it's inductive or capacitive, depending. So you will have the E field concentrated not at the top, but down here below, close to the short area. So as you can see, we can make this faster. Almost like light bulbs, you know. Each one will go to the couple to the other one. Okay. So let's see if we can look at the H field instead. So let's do that. And so it has to recompute. Okay, there we go. So you can see how the E field is the other way around, of course. At the resonance frequency, the H field will be maximum at the bottom, which is shorted, where the open sides will be the minimum. Okay, let's see how that is. Just out of curiosity, let's look at if I solve this at another frequency that's not within the band. Okay, let's see at 2 gigahertz, which is below the 3 dB bandwidth. So, let it compute. Okay, well, that's interesting. Oh, 2 gigahertz is the middle band, actually. I'm sorry, this is mid band. So we need to go say at it may have been that all of these frequencies. Okay, there we go. That's probably 1.95. Sure, in a minute. Okay, there you go. That's at the cutoff frequency. You can see that the signal comes in and never makes it. In fact, you could see that the E field even is not getting to the top where it should be. It's basically getting sucked into the ground. Okay. Now, and of course, this filter, as you can see now, as a comparison, let's say between M4 here is right at the edge, which is 1.98, and M6 here is at 1.950. Okay, you can see these little bit of a distance of a megahertz, how much attenuation down we are. We're almost 85 dB down, which is very impressive. That's a very high Q filter, of course. That's really the beauty of these filters. That's the main advantage of using these filters. Now, this is the other filter, which I will leave it for another occasion we can look at. But right now, the frequency response of that filter is like this, and it looks horrible. So I either did an error computing these values, or it just needs to be realigned. I think when I place these, I may have misplaced them right now where they are, or the depth where they are, okay? The last filter is basically one where, this. So, okay, this one here is where we use tuning to the basically the for the center frequency and for the bandwidth, the coupling. And let's see what this one. Okay, this one is same thing, so it needs to be optimized. So, ladies and gentlemen, so this is it, and I hope you enjoyed this. If you have a need, I'm an independent contractor designing RF microwave devices. If you have a need for one of these filters, let me know. I work reasonably at a cheap rate compared to US consultants. I work hourly. I can give you an estimate up ahead and just get work with you to design one of these filters if you have a need for any of these filters. Again, I appreciate you listening to my presentation. Please share my presentation if you like. Also down there, you can see the rest of the presentations. We have covered various other topics. I hope you enjoy them and benefit from. Again, thank you. This is Dr. Mohamed Nezami. Thank you. Have a great time. Thank you very much.